This video is going to explain the background material for the first week of the chemical periodicity lab. So we're going to first talk about how the periodic table is structured. As an analogy to this, if you think about a deck of playing cards, a playing card can be classified by different traits. For example, the ace of diamonds can be classified by its suit, diamonds, its value, ace, and also its color. If you were to take a deck of cards and were to lay them out in front of you in an organized way, you'd probably arrive at something that looks like this. You could take all the cards that have one particular suit and lie them out in order. So here are all the clubs in order from ace all the way to king. You can repeat that for the other suits of cards. So what we see is as you go left to right, the value of the card increases by 1. And also, in the same column, the card has a similar trait. All the cards in this column have the value of 2. Believe it or not, the way the periodic table is organized is pretty similar to this layout. Elements are characterized by the number of protons that they have. For example, hydrogen has 1 proton. So this card represents hydrogen. H is hydrogen, and hydrogen has 1 proton. The number of protons in the element, because it identifies what the element is known as the atomic number. So hydrogen has an atomic number of 1. So back in the 1800s, it was discovered that if you lay out the elements according to their atomic number, which back then was actually the atomic mass, but it later became the atomic number, certain patterns will emerge. So here I have the elements laid out by atomic number. And just using symbols right here. You probably know what most of these element symbols refer to. Okay, so there they are laid out in order. Let's look at a pair of 2 elements. So here we have fluorine and chlorine. Fluorine and chlorine share similar physical and chemical properties. Here's a picture of fluorine and chlorine. In their normal state at room temperature, they're gases. They are light green, and they have similar boiling and melting points. In terms of chemical properties, they also show similarities. For example, fluorine will tend to combine with 1 atom of sodium to make a salt. Chlorine does the same thing. It combines with 1 atom of sodium to make NaCl, which is table salt. Fluorine tends to combine with 2 atoms of calcium, and so does chlorine. So they have similar chemical properties as well. So one of the scientists who is responsible for coming up with the structure of the periodic table, named Dmitry Mendeleev, put elements that had similar chemical and physical properties into the same column. So there's fluorine and chlorine. There are other pairs of elements in this set that have similar properties. Another pair is beryllium and magnesium. So they're in the same column. Another pair, or trio actually, is helium, neon, and argon. There they are. And then we have hydrogen, lithium, and sodium. And then the rest of them. So as you can see, as you go left to right, the number of protons increases, the atomic number increases, and then in the same column, they share similar properties, just like when we looked at those deck of cards. So that's how the periodic table is laid out. It's actually pretty simple. Horizontal rows are known as periods, where the atomic number increases by 1 as you go left to right. A column is known as a group. So here are 3 elements that are in the same group. We have Cu, which is copper, silver, and gold. If you think about their properties, they do have similar properties. Copper, silver, and gold are all metals. They're all shiny. They conduct heat and electricity well. They have similar densities. So that's how the periodic table is set up. Now, the underlying reason for having similar physical and chemical properties has to do with the setup of the electrons. And in particular, we're talking about a special kind of electron. These are the electrons that are in the outermost energy level. So a very, very basic way the structure of the atom has the nucleus in the middle with electrons filling energy levels going out. The outermost electrons are special because these are the ones that participate in chemical reactions. So even though the electron wasn't discovered in Mendeleev's time, they were able to notice that there were similar chemical properties. But the reason for that has to do with these electrons. So they have a special name. They are called valence electrons. Now, an atom tends to be stable if it has a certain number of valence electrons. The reason for that has to do with energy. If I stand an egg up, it has a tendency to fall on its side. The reason for that is when an egg is standing up, it has a higher amount of energy due to gravity. When it's laying on its side, it has a lower amount of energy. So this process, going from standing up to falling down, happens spontaneously. The reverse process doesn't happen on its own. An egg doesn't just suddenly stand up on its own. So nature tends to go from higher energy states to lower energy states because of it's stable. An egg laying on its side is more stable than an egg standing up. And so this goes with electrons as well. When an atom has 8 valence electrons, all its s and all its p orbitals are filled up. That's a lower energy state. It's just the way it is. Any other number is a higher energy state, so it's less stable. So what an atom will do is it will try to get 8 valence electrons because 8 is more stable than not 8, than less than 8 or more than that. So 8 is the magic number here. And in general, that's what atoms and elements are trying to do. They're trying to obtain 8 valence electrons because that is the most stable state. And what they can do is they can give them away, they can take them in, or they can share them. And this is what's responsible for bonding. This is why atoms will hold on to each other. They can lose, gain, or share electrons until they become stable with 8. So here's an example of sodium. It has 11 protons in its nucleus. Its atomic number would be 11. The first energy level has 2 electrons, and it's filled. The second energy level can hold up to 8, and then that's filled up. So sodium has a total of 11 electrons. So the first layer has 2, the second layer has 8, and the third layer has just 1 valence electron. So if it's trying to get 8, sodium has two options really. It can either gain 7 more in order to get 8 in that outer layer, or it can lose 1. Now, a good rule of thumb is that nature tends to follow the path of least resistance. In this case, it's easier for it to lose that 1 valence electron than it is to gain 7 more. So that's what sodium tends to do. And as you'll see in lab, it does that very willingly. It is very stable because underneath, this layer already has 8. So rather than gain 7 more, it loses 1 because that's just easier to do. Now we have an imbalance. We have 11 protons and we have 10 electrons. Protons are positively charged, electrons are negative. So now what we have is an atom that has a charge. When an atom has a charge, or a group of atoms has a charge, it has a name. It's no longer called an atom, it's actually called an ion. So we have a sodium ion. It just basically means an atom that has either a positive or negative charge due to an imbalance of protons and electrons. So now the sodium atom, or ion now, is stable because it has 8 valence electrons. So in nature, this is how you find sodium. It exists as an ion because that is more stable than sodium with the extra electron. So luckily, valence electrons tend to follow a pattern on the periodic table. The reason that elements in the same group have similar physical and chemical properties is because they have the same number of valence electrons. The first group or column has 1. The second one has 2. In between, this section right here we call the transition metals. These tend to have 2. although it can vary. It doesn't really follow a set pattern. It depends on the individual element. Moving on, we have 3, and it increases all the way up to 8, with one exception. These all have 8, with the exception of helium. Helium only has 2, but the reason we put it in the same group is because it has very similar properties to the rest of them. These are known as the noble gases, and they're called that because they have the number of electrons that all of the other elements are attempting to get. So as a result, because they have 8 electrons, they are very stable. They tend not to react with other elements. Another property that's going to come up in lab is called ionization energy. So if you remember that word ion, it means a charged either atom or group of atoms. Ionization energy is the energy required to create an ion. And specifically, it's the energy required to take an electron away, to remove an electron from an atom. Energy cost to steal an electron. So there's an energy value associated with this. Here are the ionization energies of 2 elements, aluminum and sulfur. The unit of energy is joules, and because these numbers are so large, they're expressed as kilojoules. Aluminum is 578 and sulfur is 1,000. So what that means is, because sulfur has a higher value here, it's harder to remove an electron from sulfur than it is from aluminum. This property will be discussed in lab, but this just acts as an introduction. Okay, so in lab, what you're going to be doing is, we have some elements labeled on the periodic table. You're going to be looking at a couple of things. The first thing is, you're going to be looking to see how reactive they are. Then you're going to see how the reactivity of the element relates to its position on the periodic table, and if there's a pattern there. Finally, you're going to be describing how ionization energy can explain why the elements have different reactivities. The more specific procedures in lab will be discussed then, but this provides a background of the concepts.